Okay, welcome back. So as you know, we are in the week 6 of this course. So we've already covered 5 weeks. This would be the third module of week 6. So I hope that you are enjoying this course so far. So so if you remember, for the previous module and previous week, we had gone through the details of how life cycle analysis is performed. I also gave you an example. Later on in the week 8, we will look at some more examples, and we will also have some example problem solving, which will be uploaded as a separate video later on. So today we will for this particular module, we'll try to look at, when we say this life cycle analysis, if you remember, we were looking at the different chemicals, how the chemicals, what is their environmental footprint. But if you think of a realistic environmental problem where you have a release of chemicals, so ultimately why we are worried about all this? We are worried about environmental impact from human activities, including manufacturing and usage of lot of anthropogenic chemicals. When we say anthropogenic chemicals, they are man-made chemicals. They are not natural chemicals. For anything which is made naturally by Mother Earth had a mechanism to take care of that particular material that is made. But when we make lots and lots of material in our factories and dump it on Mother Earth, when I say Mother Earth, I'm essentially talking about water, soil, and potentially to air. We have to understand how these chemicals are going to behave in different media, and that kind of dictates what kind of risk it may have. So today we'll look at some of the basics of that. So topic for today is environmental release of chemicals and its fate and transport. So how the material gets released? Material usually, when say in the life cycle, if you remember, we were talking about from the raw material acquisition all the way to disposal. So at the end of its useful life cycle, or even during the production phase, so when you are doing some mining activities, so when you do the mining activities, as part of the byproduct, you produce mining overburden. You use a lot of say for example, in the fracking industry, they use a lot of water, and most of that water, when it comes out, it's highly contaminated water. So those water needs to be treated as well. So the material at the end of its life cycle, either as a consequence of production or use, when the chemicals associated with that particular material gets released into the environment. So the question is, will the release pose significant environmental or human health risk? Because if you remember what those impact categories we had, the different impact categories that we chose for the life cycle impact assessment, when we say this impact assessment, how we decide whether there is a significant risk or there is no risk. So for that, this fate and transport basics needs to be understood, and at the same time, whether this chemical will exist as it is, or whether they will degrade to newer chemicals, they will make the daughter products. And once it degrades, or even if it stays as it is, how long it will stay as it is, how persistent is that particular compound. So environmental release can happen when the things any product or material is disposed of, or during the production phase, the waste that is produced. So the question, again, the kind of question will be, what is the significant environmental and human health risk for that particular material, and whether the chemical will degrade in the environment or will it persist. So as I said, what will happen to it over time. So there are different environmental processes, as you can see in this particular table, which is taken from the book that I suggested you to, kind of one of the not required, but one of the suggested textbook, which is part of the course description. This particular table comes exactly as a table of 4.4 from that particular book. So there are whenever we look at this environmental risk screening, we look at several environmental processes, as you can see over here. We have dispersion and fate. Dispersion and fate is whether how easily the material will get dispersed into the environment. Especially, it's very much related to when we talk about the air pollution problem, how things will get dispersed, and what will be its fate. And some of the properties which is relevant to that is volatility. Volatility means how volatile is the material. So say as you open a bottle containing some organic acid or something, if you can smell it, what does it mean? It means that material, that the chemicals inside the bottle, part of it went into the air phase. Otherwise, you will not be able to smell, isn't it? Anything you can smell through your nose is only possible if things are there in the air phase around us. Otherwise, if it doesn't come in air phase, we're not able to smell it. So, and whether things will come to air phase or not depends upon whether the material is volatile or it is not a volatile substance. So, volatility is very important in terms of dispersion as well as the fate. Density of the material, why density is important? Anything which is lighter than air will have a tendency to go much higher and can go with the wind or a long distance. Anything which is heavier than air will have a tendency to stay at the bottom. If you remember, if you are pretty much sure that you must have heard about Bhopal gas tragedy. That Bhopal gas tragedy, if you know that the gas which was involved was methyl isocyanide. So, methyl isocyanide is heavier than air. So, that's why we from the Bhopal gas tragedy, we had a localized impact, but much severe impact. The impact was in and around Bhopal city, but not too much away from there, because it's heavy, it could not travel too much, but then it has a severe impact because the concentration was pretty high. It did not get mixed with the air very well. Had it been lighter than air, it could have gone up, so that the impact would have been less, and at the same time, with the air mixing, it could have got diluted. And that's on the positive side. On the negative side, if it's lighter than air, things may travel a longer distance. So, because it will travel with air. So that's but since it gets diluted, for most of the situation, you will have less impact as opposed to having something heavier than air. So density is very important for that part. Melting point, whether things will become a liquid or will remain in solid, we know that. Water solubility, how much it will be soluble in water. Something which is easily soluble in water can be carried by water. If it's not soluble, it will just stay in the solid phase. Then whether our wastewater treatment plant can remove it, the effectiveness of wastewater treatment plant. See, most of the wastewater treatment plant we have in the world today, they are designed to treat for organics. So since we have higher organics coming from the fecal matter, so they are essentially a set of aerobic and anaerobic system where we are focusing on removal of BOD, biological oxygen demand, which is essentially coming from organic load, and ammonia. So we have nitrification, denitrification, and all those things are happening. Some are doing phosphorus removal, nutrient removal, and all that. But if you look at the chemicals, the way the chemicals are being produced today, most of the wastewater treatment plant is not designed to treat for those chemicals. Many of these emerging contaminants. We are taking lots of medicines. We are taking a lot of pharmaceuticals. We are taking those pharmaceutical products. We say you take 100 mg tablet, your body only absorbs maybe 10 mg, 20 mg, 30 mg, and rest of it goes out as part of your urine or the fecal matter, mostly urine. So when it goes in the wastewater treatment plant, the wastewater treatment plant is not designed to treat all these emerging contaminants, not designed to treat for these pharmaceutical products. So, and then they end up in the water bodies, in the surface water bodies. So that's the effectiveness of the wastewater treatment is essential in terms to know what will happen to it. If the wastewater treatment plant can treat it, then mostly it will be in the sludge. And because as I have told you earlier as well in probably in several videos, that we cannot destroy anything which is on the periodic table, so we can only change its form. So if it's not in the water phase, if it's not in the treated water effluent, it will be in the biosolids. But then that's a different kind of problem. Biosolids means you can manage it much easier. If it gets into the water, the management becomes a little bit more tricky. So that's in terms of the dispersion and fate. There are the relevant properties. Many of these properties, as you can see, are repetitive because they do impact. Persistent in the environment, that's the second environmental process. That will depend on how easily it can be degraded. What is the atmospheric oxidation rate? If it gets hydrolyzed, what is the aqueous hydrolysis rate? So all those your chemical kinetics, that will essentially, like, what is the rate of reaction? And for that, remember, we use the term you must have heard in your high school or maybe in first year engineering or science courses as well. We call it a term half-life. Half-life, as you know, half life for any product means at what time, say you start with x amount of that material, if the concentration is x milligram per liter or x milligram per kilogram, by what time it will become half of x. So, x divided by 2. So, that is the half life. So, shorter the half life, higher is the degradability. Higher the half life, that means our chemical is more persistent. So, that's so those kind of rates have been given here, rate of microbial degradation and adsorption. So, all these things are relates to the rate. So, that is your chemical kinetics part. Then uptake by organism, whether organisms will be able to uptake it. Volatility, if it is higher volatility, things goes to the air phase, organisms may not be able to uptake it. Lipophilicity, what is again this is a newer term now, we have not seen it in other two. Lipophilicity is basically affinity for lipids. Remember, it is similar to, remember there is a term hydrophobicity and hydrophilicity. Hydrophobic means, phobia means fear, isn't it? Many times you say phobia of this, phobia of that. So, hydrophobic means something which is fearful of water. If anything is fearful of water, it will not dissolve in water. Very simple. Just think in a logical way. Anything which does not like water will probably does not dissolve in water. It will try to remain in the solid phase. Hydrophilicity means affinity for water. They love water. Philicity means they love water. So, if they love water, they will get into the water and they will dissolve, and then it becomes in a dissolved phase. Similarly, lipophilicity means they have a tendency to react with lipids, and if higher the lipophilicity, that means that more will be the uptake by the organisms, because in our body we have like lipids and all those things, and so this molecules or chemical, if it is lipophilic, it has affinity with our lipids in our body, it will get absorbed on lipids, and then it will build up in our body. So, that is important. Molecular size, that is another one. Molecular size is very, very important in terms of how the part will travel or how the things can be uptaken. Bigger, see, when you hear about air pollution problem in Delhi, luckily this year, this winter we did not have that much of an issue, but every winter we get an issue of higher air pollution problem in Delhi during the winter months. And one term you hear a lot when we talk about air pollution issues is particulate matter, PM, PM10, PM2.5. PM10 means any particle less than 10 micron, 2.5 means particle less than or equal to 2.5 micron. So, molecular size, the size of the particle is important. Is smaller the size of the particle, they can easily get into the body. So, it will go into our nose system. If you inside as you can feel it, there is a small hair inside the nose, and that hair has a purpose. Those small hairs are there, they act as a filter. Anything when we inhale things, any contaminant which can be trapped by this filter in our nose, it does that. But the smaller the particle, our nose will not be effective. So, that is why PM2.5 is much dangerous than PM10, and PM10 is dangerous than anything bigger than that. So, smaller the particle, it can easily go through our nose, and then it can go to our lungs. So, that becomes a problem. So, molecular size dictates how the uptake would be by organism. Degradation rate in organism, like how the things will degrade within the organisms as well, that is also important. Then human uptake, whether it will go through our dermal layers. What is dermal layers? It is our skin. So, whether say if I am touching something which is my hand has some chemicals, and then I put this hand on top of it, now whether this some of these chemicals will go through here. This hand I had a gloves, I did not have any gloves on this one, by mistake I put the hand on the gloves, and some of the chemicals from the gloves can get into my skin and get into the body. That is the dermal contact, that is the dermal layer. Then what will be the transport across the lung membrane, with how it will go with the lengths, we talked about that for the air pollution. Degradation rates with the human body, how it will degrade within our human body. So, all these factors needs to go in terms of the environmental risk screening, and then you look at the toxicity and the other health effect that gives you the dose response relationship, and I think we talked about that earlier. So, in terms of the persistent of the chemical, once the basic physical and chemical properties are defined, we can look at a series of again these don't worry too much about these slides, has a lot of text in there. This was given to you just to kind of help you for reading purposes, so that you can it's like a summary of the book chapter that you, rather than which can help you, at least I want you to at least read this. I will encourage you to read the book chapter as well, but that's why some of these like a small paragraph bullets, which is not very common. This particular chapter and some other module, you will see that I usually I don't like this way of slides, but just to give you some more information, and as you know, we'll provide you the PDF file of the slides as well. So this can add a reading material for you. So, but the basic concept, just if for the lecture part, you can always read it later, but for the lecture part, the basic concept here is the physical and chemical properties of any chemical will define whether it's persistent and whether it will get broken down, how quickly it will broken down. Then we talked about the rate. We have to estimate the rate. Rate will tell us how long it will take in terms of half-life, whether it goes, whether it, when it is reacting with the aqueous environment, what is the rate of reaction, how quickly they produce like a newer product, and the environmental concentrations can be predicted, can be estimated based on the rate of reaction, based on what happens in terms of the environmental fate. Human exposure can be calculated along that way. So we can come up with this chemical and physical properties. They can be used to evaluate a variety of metrics. We can come up with for its environmental impact and all that. So that's kind of in a nutshell how we look at in terms of the environmental release, in whether the chemical is persistent, how it will degrade, and different aspects associated with that. So now let's look at a scenario like a practical scenario which can potentially happen. So here and does it do keep happening from time to time. So if you had say you are driving on a highway and you see that on side of the road there was a truck tipped over in the previous night due to some problem or the other, the truck tipped over, and then we have a release of gasoline into coming into the system. So as you can see, if it's here, that's the top line. This kind of shows you the surface layer. So it's at the side of, you can assume it as the side of the road. The truck has tilted over, so that and there is some release of liquid gasoline. Gasoline is a petrol, and then you have this plume that you see here, light this peach color. That's your plume where this gasoline has traveled down, and then it goes, and this is the lower black line is that water table. So gasoline is sitting on top of the water table. Gasoline does not dissolve in water very quickly, so it takes time to dissolve, but it does dissolve. Part of it does dissolve, and then you can see a plume of the dissolved plume going in. In between, we can have some vapor diffusion going around between this soil. This layer between this point and this point is called Vadose zone or unsaturated soil layer. So there are we have some pore spaces. These pore spaces have some air pockets. So this vapor which is being diffused can replace some of those air pockets and take those positions. Once you go below the groundwater water table, you are essentially all those things, all those pore spaces are filled with water, because that's the saturated zone. So you cannot have things diffusing in terms of the air part, but you can have the liquid dissolving, which you see over here, dissolved plume, which is happening. And why the plume is going in this direction? Just because the very simple answer, because the groundwater is in that direction. Had the groundwater be on the right hand side, the plume would have gone on the right hand side as well, because the groundwater will carry these chemicals with it, and that's called advection. That's the phenomena of advection. So where the contaminant is carried by the media and as the media flows through. So that's your, say you had some chemicals in there, Gasoline, as you know, is not one chemical, it's a mixture of several chemicals. So BTEX is very prominent of them. BTEX is benzene, toluene, ethylene, and xylene. So they all have different physical chemical properties. So there will be some vapor diffusion, there will be some vapor released to that. And we have if you have a building, and then this is the basement of the building, or like the base of the building, and if there are some cracks, some of these vapors can make into those buildings as well. So once the vapor gets released into the atmosphere, the wind can carry it on a longer distance too, although it will be diluted forth. So this gives a scenario. This is also known as the conceptual diagram. Many times you get the concept that it's a conceptual diagram. It's a concept where it's a conceptual diagram in terms of how any release of chemical, what are the different things that will happen into the environment in the near vicinity of that particular spill. So that was one example. Now the other example, let's see if you have a leaking storage tank. That's a very common, say if you have a leaking storage tank of a radioactive waste. So there are different contaminants that can potentially leach off. Now you see these different colored graphs. These are called plume. As you saw in the previous example as well, previous slide as well, there was a plume. Similarly, here we have a plume, and for different types of chemicals coming out from these leaking storage tank of a radioactive waste, we have plutonium, we have rare earths, we have cesium, strontium, ruthenium, and also nitrate. So based on their physico-chemical interaction with the soil layer, with the media which is there on this side, like based on their interaction with this different the soil media, we see that different chemicals from this radioactive storage tank, radioactive waste storage tank, does travel differently. So we had a travel of different, if you look like plutonium had traveled very less, then the rare earth, then the cesium, then strontium, ruthenium, and the nitrate. Nitrate is actually easily dissolved in water, so it can travel with water much quicker with any soil water which is present. And but these other elements which was there in this radioactive waste, the reaction, based on the reaction with the soil media, the things will behave differently. And then as you can see in the figure, we had the monitoring wells. So how we'll decide how we draw these plumes, as illustrated in the figure. As you can see that we have different plumes, boundary has been defined, and these are based on these kind of monitoring wells. So you have to do a series of monitoring wells across this contaminated site to give you an idea of how far the waste has traveled, how far the different chemicals have traveled. So that's we can model. After we get some of this data, we can also model and to try to find out that how long it will take for some of these contaminants to travel all the way to the groundwater level. So after we collect some basic information data from our experiments, we can do this. We can do that exercise. Another example, say if you have a landfill kind of condition, you have a leaching waste, waste is leaching off because of the different chemicals leaching, then you have a groundwater flow in this direction, and you see a kind of a plume building up. And again, the different chemicals will be there, but they based on their affinity for the soil, affinity for all the things that is happening there, and their interaction with different media, the plume will have kind of different stretch for different kind of chemicals. In the natural environment, there are when we talk about any of these organics, especially organic chemicals or organic matter, when they get released into the environment, one of the thing is they have to degrade. So organic matter degradation essentially means that things are moving into organic matter gets oxidized. So when they are oxidized, something has to get reduced. So when things have to get reduced, there has to have a electron acceptor. Remember from your I will not go in detail on that, just to you revise that part of your chemistry if you don't remember that. So once there is any reaction, we have a one in oxidant as well as oxidation and reduction happens at the same time. For oxidation, there will be an like a release of electron, and in reduction, electron is accepted. So if you look at this sketch again, so first you will there are the reduced species are created based on, in the aerobic respiration we have the water, which is the reduced species. Denitrification, you have ammonia and ammonium ion. Then you can have manganese reduction, iron reduction, sulfate reduction, and then finally methanogenesis, where you produce methane gas. So those are and these are the oxidant being reduced. Here we have oxygen, then nitrate, then manganese oxide, then iron oxide, then sulfate, then CO2. So these are what it is getting reduced, and based on this based on the EH of the EH means the redox potential of the system, we know which one will be preferable system for reduction, and that defines how the waste will behave in a natural setting in terms of its reduction going on. Other then again this couple of slides more, where we have kind of given a very basic definition of what is melting point, what is boiling point, what is vapor pressure, and you all know about all that. This is just to give you a recap of what they are, because you know the melting point is temperature at solid and liquid coexist. Boiling point is when it goes from the liquid phase to the vapor phase. Vapor pressure is the partial pressure exerted by the vapor when the vapor is in equilibrium with the liquid. So those are there, and that how we use it, those informations are also provided just for your benefits. Some others, Henry's loss constant, octanol water partition, water solubility. So these things needs to be kind of revised if you have forgotten about it. Same thing with the Soll sorption coefficient or the bioconcentration factor. Soll sorption coefficient is the equilibrium ratio of mass of compound absorbed per unit weight of organic carbon in the soil. So that's kind of gives you a how good the absorption will be in case of any chemicals passing through certain soil layer. So you can do the partitioning of solids and liquid phase and all that kind of stuff. Bioconcentration, it basically say how the things will concentrate along the food chain. So all these probably we already kind of know about that. So we try to, based on we have to essentially do some estimation in terms of environmental partitioning, persistent, and measure of exposure. So that we take as we know, the environmental exposure are complex. So but if the chemical is released in a river stream of the public drinking water system, so that will be drinking water contamination will be a problem. So some of the questions that we need to ask about that is what fraction of the chemical was absorbed by sediments, what fraction of chemical was volatilized, what fraction of chemical was taken up by living organism, what fraction of the chemical was biodegraded or we lost, what fraction of the chemical was removed from the treatment process. So all these questions needs to be answered when we are trying to do this environmental characterization and risk. So kind of in summary of kind of summarize this with this last slide on this particular module. So we have to get the information about the different properties, and that helps us to characterize the environmental risk. Chemical and physical properties, as I listed few of them as well, they can be used to estimate environmental footprint, and which is again all these information kind of already goes into this LCI. When I say that you can use certain database, where you can use certain impact assessment method, so all this information is already built in those tools. So that's why it's important for you to understand what goes on behind that software. Software does things for you, but if you have to tweak that software, if you have to use it for your own kind of a set of criteria, you should be able to tweak the software, and in that case you need to understand some of those basics. So chemical and physical properties are important, which we talked about. Another approach is to use the values of property directly to characterize the environmental risk, and then we classify it whether it's a persistent, bioaccumulation potential, and all that. So there are some in this next two slides, which just are essentially maybe 3 or 4 slides. What we have is some information available in terms of what is the water solubility, what Soll sorption, what is a strong sorption, it's moderate sorption, and all that, biodegradation rates, bioaccumulation potential. So different numbers are given, and based on that we can choose which one kind of does better than the other. And then you can have different types of fuel molecules. Bigger the molecule, bigger the benzene ring, very quickly it will degrade, it will be hard to degrade. Long chain compounds, it does degrade to smaller chain compounds, so those kind of things are there. So these are different types of fuel molecules are present. And there is this particular say if you one problem is one kind of question has been put forward here, that if you compare the salt sorption, water solubility and biodegradation of 3 compounds which in gasoline, which is ethanol, MBTE and isohexane, we can assess if chemical is spilled on land, would be more likely to migrate the surface or groundwater. So depending on its solubility and all that, isn't it? So here are the data which is provided. So based on this data, since the salt sorption is given to us, based on salt sorption we will know that higher the salt sorption, that means more will be the concentration in the soil phase. More the water solubility, that means more has the chances to go into the water phase. And in terms of biodegradation, if it's quicker, that means things will degrade faster. If it's a longer half-life, so it will take long time to do it. So based on that, it's if you look at the data, the results that petroleum, if you have a spill, you most likely that MTBE is a spill on the ground, more likely to absorb to soil. The petroleum gasoline will goes into the soil than MTBE and ethanol, making it less likely because of salt sorption. And in contrast, however, MTBE ethanol added to gasoline because of those like reducing of emissions and all that. So just to kind of gives you some idea about, based on the salt sorption, water solubility, you can predict whether things will end up. So with that, let's kind of wrap this particular module. It was and then I hope this kind of gives you again, as I said earlier, these we are for many of these topics we are able to just do a quick overview of the topic, and we will be more than happy to answer any questions. The discussion forum is already on, so you can raise questions over there. We'll be able to answer to your questions, and I'll encourage you to look at some of these freight and transport basics. So there would be other sources of YouTube videos or books and other stuff. So I will strongly encourage you to do that, because those are very much related to how we do this life cycle impact assessment and what are things needs to go in inventory. So okay, thank you, and I'll see you again in the next module.